Hello everyone. In this video we will be discussing about bitwise operators. Very important and interesting topic. Bits. What is meant by bits first of all? You know that computer can understand binary language. What is binary language? Which is in the form of zeros and ones, right? Zeros and ones. So we are dealing with those zeros and ones in this particular video. Okay, very first let us see what are the bitwise operators we have. Thereafter we'll go one by one. Very first, bitwise AND is there. The representation of bitwise AND operator is like this. Next one is bitwise OR. Bitwise OR can be represented with the symbol like this. This one. XOR, you can write XOR simply. EXOR is not compulsory. XOR also sometimes can be represented. XOR operator is symbol is this. Okay, so right shift operator, left shift operator, and bitwise NOT operator. So these are the bitwise operators we have. We need to work on each and every bitwise operator, and we need to know why a particular result we are getting by applying bitwise and how we are getting that result also. Very important. So in order to understand deep level of coding, these models are these kind of operators are very essential, and we should know everything, how we are getting the result, how we are getting the output. So let us get back into one by one each and every operator. But before knowing or working on the bitwise operators, we should know how the binary number representation can be done. For example, 12 is given. For example, 12, number 12 is given. How that 12 number can be written in binary form? In form of binary means zeros and ones. Na? How we can write that? I am showing one example here. Binary number representation. Okay, very first I will explain that. My topic is bitwise operators only. But before going to each and every operator, I will be explaining here binary number representation. Okay, for example, the 70 number is given to you. Okay, the number 70 is given to you. So 70, how I am writing is, look at, these are the representation of how we have to write these numbers. 2 power 0, which is 1. You just ignore what I have written here as of now. 2 power 0, 1. 2 power 1, 2. 2 power 2 is 4. 2 power 3, 8. 2 power 4, 2 power 5. 2 power 6, 64. 2 power 7, 128. If I need more and more numbers, you can write 2 power 8, 2 power 9 also. And see here, I need to get 70. Out of these all numbers, you just pick some numbers so that I will make addition 70. 64 plus 4 plus 2. 64 plus 4 how much? 68 plus 2 how much? 70. Number 70. Just across those numbers where you have considered for getting 70, above 64 you put 1, above 4 you put 1. Why? Because 64 plus 4, 68, plus 2, 17, plus 1. So 1 you consider. Remaining all the places you put 0. Why? Because you are not considering them. Whatever the numbers you are considering for getting the result, decimal number or number, those number places only we have to put 1. Remaining places we have to put 0. The arrangement should be like this. Rightmost to leftmost, 2 power 0 starting, 2 power 1, 2 power 2, 2 power 3, 2 power 4. It is not compulsory that always you should write this much big. You can write 8421, 4 bits code also. Okay. So how I written 101000110 is the binary number representation for what? 70. For example, let us consider these 4 bits only. Let us consider these 4 bits. 0110, right? So what is the this normal number, natural number? What is the natural number for this? 0110. What I will be answering is 8. At the place of 8 you kept 0, so I am not counting. At the place of 4 you kept 1, so 4 plus at the place of 2 also you put 1. 4 plus 2, 6. At the place of 0, sorry, you kept at the place of 1 you kept 0. So 1 is not counted, 8 is not counted, 4 plus 2 is counted. So up to here the answer, if you are asking me 4 bits, what is the answer? I can say 6. Hope you are understanding what I am trying to do. Okay, so let us now, from with this basic idea what you have what you are getting for binary number system, representation. This is very very important first of all to not to need to work on the bitwise operator. So be careful in writing the binary number for the given numbers. Okay. So for example, I am writing like this: 0, 0, 0, 1. Okay. I am writing like this. So up to here you observe, I have written 1 only under 8. Remaining all places after that, I have written zeros. Means I will be counting 8. So for this, what is the number? What is the natural number we are getting this? 8. What is the natural number we are getting for this? 8. For example, I am writing one more number. Just observe here: 1, 0, 1, 1. And for this, what is the output we are going to get? Count 8, count 2, count 1. 8 plus 2 plus 1. What is the number we are getting? 11. Like this, binary numbers can be converted as decimal numbers, we call it natural numbers. And these numbers also can be converted as binary numbers like this. Okay, do remember, this is very very important. Now let me shift to bitwise operators. Okay, so bitwise AND operator, very first, this is the symbol we are using. Okay, so very first let us see the truth table. This is the truth table. We say if we have two zeros in bitwise AND operation, if we have two zeros, then the result is 0. Okay, if your end na both should be 1, like this, both should be 1 to get the answer 1. Remaining all the cases, the answer will be 0. A value should be 0, B value is 0, then answer is 0. If A value is 1 and B value is A value is 0 and B value is 1, then also 0. So and you are using na both should be 1, both should be true. 1 in the sense true. False, false, false. False, true, false. Why false is and. Both should be true. False, true, false. 1, 0, 0. Both are 1. True, true. That's why answer is 1. So you observe here, bitwise AND operation I am doing. I have written the binary number representation for 2 and binary number representation for 6. Now I am doing AND operation. From here you have to do 0 and 0. What is the value? 0. 1 and 1. What is the answer? 1, 1. 1 and 1. What is the answer? 1. That's why I have written 1 and 1, 1. 0 and 1, 0. 0 and 1. What is the answer? 0. 0 and 0. Answer. What is that? 0. And can you guess what is the output for this? This is the output we got it. And what is the answer? The answer is 2. Bitwise AND between 2 and 6 is, the answer is 2. You observe, you see this in real time example. I am writing int a equals to 2 comma b equals to 6. These are the values given, right? Here I am writing, let me take out one more variable, c equals to a and b. Printf, I am printing only c value, percentage d comma c, and see what is the output I am getting. The output I am getting here is 2, but many of us doesn't know how we are getting this answer 2. The story behind, the logic behind this is this slide. Bitwise AND between 2 and 6 is, this is the answer we are getting, and this is the natural number for this is 2. That's how we got the answer. You just see here. Again I am showing answer. The answer is 2. Look at here. And now let me shift to the next operator, Bitwise OR. So the symbol used for Bitwise OR is the straight line. You can see this straight line above the enter button in your keyboard. Okay. So OR is quite interesting. If at least 1 is there, at least 0 or 1, answer will be 1. Well, coming to AND, we just look at AND. Both should be 1 to become 1. In all remaining cases, your answer is 0. But in case of Bitwise OR, if at least 1 is there, then answer is 1. In order to get the result false 0, both the values should be 0. 0 and 0 or 0 is only 0. Remaining all cases 1. Now let me see the example for Bitwise OR. A value is 10, B value is 7. So binary representation is this. You can see in the starting of this video how the binary representation I have explained. The similar way it is converted to binary number, and 1010 is 10, and 10111 you can write left side 0. So you are performing bitwise OR operation between these two. 0 or 1. What is the answer? 1. 1 or 1. The answer is 1. 0 or 1. Answer is 1. 1 or 0. Answer is 1. You see, 0 or 1. Answer is 1. 1 or 0. Answer is 1. Like that we are getting answer. 1, 1, 1, 1. Which is the final answer we are natural number or we are getting here is 15. We call it as a decimal number here. In mathematics, decimal number is 2.5 like that, but here decimal number is not that. Natural number we call it as decimal number. When we talk with binary number, na, the converted natural number will be calling it a decimal number. And let us see the same example in the system also, what the system is giving. 10, A value is 10, B value is 7. Na? I am giving to the system. A value is 10, B value is 7. And what is the operator used? Not AND, it is OR. Bitwise OR operator is used. And what is the answer we are getting? 15. And you see in this slide, the answer we are getting here is 15. Internally this is happening, but system is giving that. We should know what system is giving, what kind of answer it is giving. We cannot be in a feeling like system is giving answer now, then what is there to worry. We should, if you have to write the new code, then we should know how the system is performing, right? So that's why we should know all these things. Okay, so now the next one, bitwise OR or bitwise XOR. This is quite interesting. XOR easily you can remember. If two bits are same, A and B are same, then only answer 0. If two bits are different, the answer is 1. Two bits are different, answer is 1. Two bits are same, answer is 0. If two bits are same, answer is 0, otherwise 1. So again, A value 10, B value 7 given. Same example taken. 0, 1. Two bits are different. That's why this answer is 1. Two bits are same. Answer is 0. Two bits are different. Answer is 1. Two bits are different. Answer is 1. 1, 1, 0, 1. 1, 1, 0, 1 is the binary representation for the number 13. And the same thing I am applying here. You see, XR how we have to apply is shift plus 6. Shift plus 6 you press, that symbol you will get. This is not power, this is XOR. And what is the answer we are getting here? 13. And you can see in the slide also, what is the answer we are getting here? 13. Okay. So now, let me shift to the next one. Hope you understood what XOR is. So far I have discussed about Bitwise N, Bitwise OR, Bitwise XOR. Next one, left shift operator. This is the symbol, less than double time we have to write left shift operator. For example, your value is 101. If you are asking to perform left shift for one time, this one will come to the next place like this. This one shifted to left. And at the place of 4, 1 is there. Na? This one will be shifting to at the place of 8. And 2, at the place of 2, what is that? 0. It will be shifting to left. 4. When you are performing left shift operator, you just start from here, left to most side, not right most side, left to most side. From there you need to shift here to here. This will be shifting to 4. At the place of 1, 1 is there, that will be shifting to at the place of 2. And remaining this place you can put 0. So 101 is the value given. If you are asking to perform left shift, it has become like this. The original value is given is 5. After performing left shift operation for one time, it has become 10. Okay. Again, if you are asking me to perform left shift operation for this, again you see here, this one will go to the place again. So again, don't take this example. So this will become next to 20. Okay. So this will come here, this will come here, this will come here, this will come here, and it will be 20. Directly one more time here we have done for 10. For every, simple to remember, for every left shift operation the value gets doubled. Okay, I'll show you with example, that is better. A value is given. Okay. uh, what I should write is, I will write like this. or let me take down one variable c equal to a left shift of one time. I have to write like this. Left shift for one time means we need to represent like this. What is the output I got it? 20. Let me give 5 first of all. 5. Obviously left shift you are performing, it will become 10. You see, for every left shift operation the value gets doubled. Now I am writing, instead of 1 I am writing 2. It means that you have performed a left shift operation for how many times? 2 times. Means 5 becomes 10, and after becoming 10 again double 20. The answer should get be, we should get answer here is 20. Now I am doing left shift operation for third time. 5 should become 10, 10 should become 20, 20 should become 40. The answer should be 40 now. 3 at each left shift operation, the value will become 40. Internally how it is happening? Like this, shifting. 5, 10, in middle one step is missing here, 10 to 20, 20 to 40. Okay. So now let me shift to the next one, right shift operation. Again it is quite opposite. So from here you need to shift it to right side. This is 0, it will go outside. From here this value will come to here. This value will come to here. This value will come to right side. Means moving the bit one place right. You may ask me, what if the first bit is 1? It is going out of boundary, so don't, you can neglect it. Okay. So 14, after performing right shift operation, it will be like this one will come here, this one will come here, this one will come here, and 1 1 1, 4 plus 2 plus 1, what is the answer we are getting? 7. You can observe here, for every right shift operation the value is getting half, for every left shift operation value getting double, for every right shift operation the value is getting half. Again you see, again one more time we are doing here, this one will go out of the boundary, this one will come here, this one will come here, and 7 will become 3. Right shift operation. And the same I am doing with the example coding. So I have to write like this, right shift, the symbol, for one time. Okay, let me give the value 20. 20 right shift, you know, for every right shift the value gets half. Do remember, the value became 10. Again I am doing right shift for 2 times. 20 should become 10, 10 should become 5. The answer should be 5. Now look at, the answer is 5. Like this. Like this we can easily check the results with right shift operation. And after that, at last we have bitwise NOT. This is a congruent symbol, and for this don't think much. If the input value is given 5, the output will, you will get it as -6. If you give the value 10, it will become -11. A equals to 10 I am giving. Congruent A. Okay, you see what is the result I am getting? 10 I am giving. What is the output I am getting? -11. And let me give 20. -20. Okay. 25. It will become -26. Like this. So this is about bitwise operators. See how easily we have discussed about bitwise operators. So far we have discussed about each and every operator: bitwise AND, bitwise OR, bitwise XOR, bitwise right shift, left shift, bitwise NOT. Okay, very first we have seen binary number representation. After that, bitwise AND with example, with execution example, bitwise OR with execution example and theoretical discussion how it is getting converted. Okay, so bitwise XOR we have discussed, left shift we have discussed, right shift, and at last bitwise NOT we have discussed. Hope you understood the bitwise operators concept. Thank you guys.